Hello, everybody. We're going to look at how you use similar triangles, kind of a class activity. I'll go through the ideas of the three ways that you could use similar triangles to measure distances that would be hard to measure otherwise. Sometimes they call them like inaccessible heights, things like that, right? Which you can use similar triangle properties to determine the values of. I'll go through the three classic types, and if you can get out with a measuring tape and a mirror and stuff like that, and do the activity, it'd be kind of a fun way of checking your knowledge and ability to use the information. Worst case scenario, of course, you follow along, do the activities. Here's a picture of one of the activities from a class that I've done. But here's the question sheet to do with it. So you can imagine being near a pond and measuring values and so on. All right. So here we go. One of the classic ways of using similar triangles is to sort of stand so that the top of your shadow lines up with the top of the inaccessible height shadow. And so in which case you have measurements, from where you are to the tip of the shadow, and where the tall tree is to the tip of the shadow. So you have sides on similar triangles and corresponding sides of similar triangles, and then you have your height if it's a known height, and maybe this unknown height you don't know, right? So if we were to set up the similar triangle ratio, by the way, we're very soon to be talking about how we know they're similar, but I'll get to that later. So we have this red triangle here as one of the triangles. The blue triangle obviously has the bigger same shape, so therefore similar triangle. And there's certain information required to guarantee that triangles are similar. We'll get to that soon. But for now, we can just say, well, we're looking for the height of the tree. So that's the unknown right there. And so if we went height of the tree over, say, the base of the big blue triangle, so number 3, then you could do the known height of the person, number 2, over the distance to the shadow tip from the person. Obviously, all those numbers are known. You can just solve for the missing piece, right? So here's a number example from a previous class I've done. And so in this case here, you'd be saying, okay, well, I want to know this height. So the color might work good for this. So the height we're looking for of the building, kind of hard to measure that. We're not allowed to go up the roof and dangle a string or something, stuff like that. So h over. Now notice here, if I wanted to do over the base, the way the students measured this, they measured in 2 parts. So they measured there, the building to the person was 8.4 meters, and then from there to there. And so what would the students have had to have done to set up a set of triangle sides for a ratio here? Press pause, try to figure it out, whatever. And then hopefully resume here and think, okay, well, I'd have to combine those, right? And so I would put this as the height of the building over the combined distance here, 2.4 plus the 8.4. Bits, and then we do the height of the person over the distance, the height of the person over the distance of just that, right? So the 1.8 meters to the 2.4. And so in that scenario there, you could add those numbers together, 8.4 and 2.4 is obviously 10.8. So you multiply both sides by 10.8. So this is obviously 10.8. Multiply both sides by 10.8. And get that canceled out. We have the height that we're looking for the building, 1.8 times 10.8. About 2.4, yes, 8.1. Right, I guess. I don't know if the scale is actually right there, not to be honest, but yeah, but that's it. Okay, so start the height. So one of the things I've had in the lesson was to get you to try and get you to think of math or see math in the world around you. So if you see this picture, what could you do, right? Well, if you did know the height of this tree because you were there when they put it up and it was like sideways and you measured it or whatever, And then you have shadow lengths of the tree and the shadow of the very top of the building. You know, you could figure out the height of the top of that building. Kind of hard to do otherwise, right? But the math we know will allow that to us to do, right? So there's, you know, here's another one to do this. So obviously we could just use the two shadows. It might be kind of hard to find the shadow of that building if you're searching through the neighborhoods or the grounds around the building. And so here's another method that could work. If you had a mirror with you, you put a mirror on the ground, or maybe there's a puddle on the ground, you use it as a reflective surface. Puddles work actually better because then they're perfectly level, right? But anyways, if you did, and you set the mirror, then you move it back until you could look in the mirror and see the top of the building, you actually set up two similar triangles. So if you set up two similar triangles there, let's label these as number 1, number 2, number 3, unknown height. Okay, so if we have those are similar triangles, and it should be pretty obvious that you got the height of the building. We could do it this way, make it more obvious, I suppose. We could height of the building over the height of the person. So height over number 1, and then obviously the big triangle for the building would be height, height of the building, and then the other one then beyond this triangle would be number 3 for the number 2. And again, you could multiply both sides by number 1 and solve for h. Right? So that's a mirror version, which is kind of different. Here's a number example from my class. And so I did the work here. We have this unknown basketball rim height. So unknown basketball height over what? Well, we could do over the other height, or we could do over the bottom triangle here. Right, so if we did height over bottom, we do the other height over bottom. Right, in which case we're multiplying both sides of 14.2. Canceling that out, leaving us with just the height that we're looking for. So you can check, you do 6 times the 14.2 divided by 8.5, and that will give us 10.0 something or other, right? Rounding close. So the the confirming the height of the basketball net is supposed to be 10 feet, right? So read out it's the right height and so on. Truthfully, that made up the numbers, but you get to a process like this. So some of them are more realistic, is very doable, obviously. Here, a picture that just the math that would go along with this, is it realistic to actually, measure the height of a cliff with ship or rock and so on? Maybe not, but the math certainly would still work. All right. So your work to practice and submit are these ones. They're all that same idea. Keep in mind, when you're trying to figure out the similarity to triangles, you've got to try and figure out which side is which here. So for this one here, if you said A, B, you did a triangle A, B, E, right? So A, B, E, right? Starting at the 90 degree, going around the long tip to the middle. Looks like we go C, D, E, right? Similar triangle C, D, E. That one, so you could line them up. We did like we did in previous lessons and so on. So as long as you can identify sort of which sides correspond to which, you just go ahead and do the normal similar triangle work. Okay. Hopefully that helps. Let me know if you have any questions. Yeah. Good luck. Talk to you soon.